Hello and welcome to Toddcast number 62. As it were, we're going to go all the way to Toddcast 63, meaning this is the next to the last one. And this one and the one tomorrow actually are going to be tomorrow. The next one, I should say, are going to be pretty much just a ton of memorization of different ways one or two reactions will work. So I will two reactions this time. I'm going to do the Wolff-Kishner reduction. We've kind of looked at it a little bit. We started into it. We looked at hydrozones. And then a reaction known as the Wittig reaction. Incredibly useful synthetic reaction. It'll be our third way to make a carbon-carbon bond. And so if you go back a few podcasts to where we discussed different nucleophiles and how these nucleophiles can attack carbonyls, the three carbon ones you dealt with were an alkyne that can attack, a Grignard can attack, and then the Wittig. So there's going to be three ways to make new carbon-carbon bonds. And so that's just something to see in the big picture. And again, this all builds up to just building a pool of reactions that can be done or applied to make, I don't know, different synthetic products. So with that in mind, let's go ahead and get started. So the Wolff-Kishner reduction, you can reduce carbonyls. We learned how to reduce carbonyls to alcohols by adding lithium hydride, sodium borohydride. Those would reduce it down to alcohols of some sort. Got rid of one bond from carbon oxygen. The Wolff-Kishner reduction is going to get rid of two bonds to oxygen. And so it's done under basic conditions. Initially, you can add it on acidic, but it's ultimately going to be done under basic conditions. There's alternate ways we discussed briefly known as the Clemenson reduction, which does the same thing, can ultimately turn a carbonyl into an alkane. And that's going to be done under acidic condition. And there's one with sulfur reagent. We didn't discuss that one, but you can use sulfur and under neutral conditions, something called rainy nickel and reduce it. So this is the only one I want you to be aware of for this class, but know that there's always multiple ways to do the same reaction. And you have to have this because of all the different potential reaction conditions something may occur under. Okay, so that said, we have a nitrogen nucleophile, and I could pick either nitrogen to be the nucleophilic one. But if it goes on, we'll do the magic water box, the magic disappearing water trick. If I lose these two H's and that O, then we're left with this N and an NH2. And emphasize the lone pairs. And what I want to focus on is the second step. So taking this hydrazone and then turning the hydrazone into an alkane. So we're doing it in the basic conditions. And so again, whenever you're coming to a mechanism and you're dealing with carbonyls, acidic conditions are protonate, break, make, deprotonate. Basic conditions are reverse to that. Deprotonate, make, break, protonate. So first step's going to be deprotonate. So this OH minus, KOH under aqueous conditions will turn into OH minus. That OH minus will come in, pull up an H, deprotonates it, and it with a lone pair, second lone pair on the nitrogen, and a negative charge on the nitrogen. So important to note that in mechanisms dealing with basic solutions, basic environments, all your intermediates, all your compounds must either be negatively charged or neutral. Under acidic conditions, everything should be either positive or neutral. So here's a case where you have a negative and a neutral. Keep track of the fact that you have to have a negative in the end. So we'll end up with water, H, OH minus, and this H coming off form water. So that's now neutral, which means the negative has to be on that N. So there's my deprotonate. So now we need a make and break step. So the make is going to involve this nucleophile coming in and forming a pi bond. The break is going to be that pi bond breaking. So here is my make. Here's my break. And then finally, last we need a deprotonate. So this compound we now made with a negative charge here. And note, I really should indicate that this is a double arrow because that's a resonance structure. In this case, then, we now have a negative, just going to protonate. So the water we generated in the first step is going to be consumed in the last step. And when it does, we have our protonate step. So we deprotonate, make, break, protonate. Because I have two bonds that I need to deal with, I only did one break step so far, and I only put on one H, so one protonate step. I have to do it a second time in order to get rid of the 2 bonds of nitrogen and put on 2 H's total. So we're only halfway done. So we've done 1 round of deprotonate, make, break, and protonate. So time to do round 2. Same story again. The base is going to come in. Step 1, it's going to deprotonate. This negative charge here, again, negative charges on the intermediate and basic conditions. It's going to come in and make a pi bond. It's going to break. So now that's not actually a resonance structure any longer because we're breaking a sigma bond. So we again have a make and a break step. Last step to do, protonate. So again, water is going to come in and be the source of a proton. That negative charge can attack the water. We regenerate the OH minus, and we have our product. So it's a fairly straightforward mechanism. And again, just keep in mind, it's 99.9% chance the mechanism is either protonate, break, make, deprotonate, or deprotonate, make, break, protonate. No, it sounds like almost the same thing, but it's just acid is the backwards of base. Okay, so final product, your alkane. Again, this is under basic conditions. Okay, so on to our second reaction, the Wittig reaction. The Wittig reaction is, again, incredibly useful synthetically, and I would dare say probably, from a pragmatic sense, one of the probably 10 most important reactions you're going to learn in organic chemistry if you were going to go on and be a synthetic chemist. But let's look at what it is first. So as mentioned, it's a carbon nucleophile. The carbon nucleophile here we show as a pi bond, but it's also in resonance with the di-ion. So we have an anion on the carbon and a cation on the phosphorus. Just like nitrogen can handle a positive charge, phosphorus can as well. So this carbanion next to the positive plus, or the positive phosphorus with a plus, it's actually your active nucleophile. So again, this isn't balance between these two. It's a resonance form, although this is a more stable resonance structure. This is actually stable enough to be present, so much so that that's going to be my active nucleophile. Okay, so very interesting mechanism, the way it works. So I'm going to draw the negative and positive version of it. And again, you're welcome to draw it as a pi bond if you wish, totally up to you. But they come together and they have to line up the right way. So you're ultimately going to make a phosphorus oxygen bond. So if you think of stable compounds, phosphate, sulfate, borate, those are compounds that are very stable in their oxide forms. So phosphorus being in the element in phosphate means phosphorus would rather bond to oxygen than most other atoms because it naturally occurs as a phosphate. So it must love oxygen. So being oxophilic, the phosphorus is going to want to connect to the oxygen. However, it has a positive, so the oxygen has to donate into it. This negative then can attack the carbon with a delta plus of the carbonyl. We're going to see these electrons go that way. Simultaneously, these electrons go that way. So I'm going to get rid of my arrows, let the computer generate it. So again, here's my nucleophilic attack to carbonyl. This kicks up. That's going to come over the phosphorus. You have this intermediate. Now I've drawn it with dashed lines to indicate that this is partially formed. This is partially formed pi bond. This is partially formed sigma, partially formed pi. And it lines up this way. This is essential because this leads to the stereochemistry, or if you will, the geometry of the intermediate leads to the geometry of the product. Okay, so we have this intermediate. Phosphorus wants its bond to oxygen, so it is going to eventually break and form this bond right here. Is going to become a full-fledged covalent bond. And you're going to end up with another full-fledged bond here. So if these things move over that way, you're going to take the electron density between the phosphorus and carbon, end up between the two carbons. Oxygen is going to end up with phosphorus. So it's the alignment that matters. I've actually sort of sped this up and had the electrons move over twice so that you have this bond situation here. But the key thing is to recognize the way we have these molecules lined up, it's going to force an issue with steric hindrance somehow, some way. Okay, so they now move apart. your phosphorus with the oxygens, you have two R groups on the alkene, you're set. Things to pay attention to. This pH stands for a benzene ring, which is absolutely massive, which means there is significant steric hindrance, and there is also significant resonance. So the benzenes can donate a pi bond to this phosphorus, and you can actually stabilize this carbocation or phosphocation by sharing with these rings. So the ability to have something donate electron density into the phosphorus is going to make a difference. And then the second thing is, depending on how crowded these R groups are, so two R's on this one and two H's on this one, didn't become an issue. But if this was an R and an H, if this was an aldehyde, and let's say my Wittig reagent had an R group on it, how those R's line up in the transition state becomes important. Okay, so let's see it in action. The stereoselectivity, or geometrical selectivity, depending on how you want to word it, is going to come into play. So let's figure out how we make this phospholipid. So we're going to have the phosphine, triphenylphosphine, that lone pair is going to attack there and kick out the I leading group. So it's just a standard SN2 reaction. Then we're going to treat that product with a base. It's going to deprotonate the carbon. So it's got to be a very strong base. And as you know, when it's a strong base, you have a few choices. You could use Lin, or you could use Bully. I'm going to choose this one. So N-Bully is going to come in. It's going to deprotonate one of these H's, and you're going to end up with this species mentioned before, which is in equilibrium with the double bond between phosphorus and carbon. Okay, so we have this. So again, these resonance structures, equilibrium is the wrong word, but I should just say that it's resonating back and forth, and you have your major and minor contributors. So now it's time for a Wittig reaction. Once you have this Wittig reagent, and so let's say you create, again, like I mentioned, an R and an H. So you have two separate entities. So in the triphenylphosphine compound, or the compound up here made from the triphenylphosphine, and have an H and a CH3, and over here I have a benzene ring and a carbonyl. So in theory, you could line up with the two H's on the same side and the phenyl and the CH3 on the same side, or you could end up with CH3 and the H on the same side, and the phenyl and that H on the same side. So this one, it's pretty tricky to get, and so I'm not going to actually test in much detail on this, other than you'll recognize when you have more electron donating groups, you have a tendency to get more of the trans product. When you have less donating groups, you have more tendency to get the cis product. So the major product in this case ends up being Z, because these aren't terribly good at donating. This is okay donator, benzene's not bad, but that's not a great donating group. For our next reaction, you'll notice I have a donating group. Now I have an electron withdrawing group. So if I have a donating group on the phosphorus here and a withdrawing group on the carbon over here, electron density is shifted over from the phosphorus to the carbon, which it is because of this electron withdrawing group. We now have a tendency, the transition state will line in a way where we end up with the trans, or if you will, the E product. So the other example we have particularly bulky groups, like the two phenols that have a tendency to go trans. So you're probably sitting there and thinking, it's kind of hard. There's a lot to memorize here. There's no real rhyme or reason. The one thing I really want you to be able to just take note of is that if you have an electron withdrawing group, that group in particular, it influences the formation of E. The decision of how steric hindrance will affect it, I'm going to sort of leave that one alone, and we'll talk about it in class, we'll do some examples, but it's not necessarily reasonable to test it. But electron withdrawing group on the phosphorus-based reagent, the Wittig reagent, that we will care about. Okay, variation on it, because Lord knows we don't have enough variations on this one. Okay, so we have the typical one. This is the resonance stabilized Wittig reagent. So as mentioned, this withdrawing group can help these electrons to be stabilized here, which keeps electron density on the carbon side, which makes the phosphorus remain positive, helps it align in such a way that you're going to end up getting it trans. Horner, Wadsworth, and Emmons, they did a very similar reagent. So you'll notice it's still a drawing group, still an ester, only this time they did a methyl ester instead of an ethyl ester. Not that much different. But what they did is they have two donating groups and one severely withdrawing pi bond on that phosphorus, as opposed to having three bulky groups. So reduced steric hindrance, that's going to help. And then also electron density distribution is going to help as well. So no longer do we worry about the positive charge on the phosphorus, but we do have a withdrawing group. And then this negative charge on carbon is going to resonate up. So when they use this reagent, it ends up that withdrawing group, this R group, ends up trans to the R. So you can design your reaction to have a trans product. So if you need trans, do it that way. If you need cis, well, you run with it. You figure out how to align it with a smaller group and let the non-withdrawing group help with it. Okay, so time to predict some of these. So when you look at this group here, we have two R groups, one small, one large. This one is fairly large. So in this particular case, you need to worry somewhat about steric hindrance, but as it were, it's not as big as a phenyl group. So this one's going to align. And when it does, it's going to end up aligning cis with respect to this bulkier group. Okay, so far so good. So that would put this bulky group over here, aligning with this smaller CH3. Next one we look at. We're lucky in this case because we have something symmetric. I don't really have to worry about it. I get a free pass on this, but just make sure I note this group's going to come in transition state and be near one of these. The H is going to be near one of these alkyls. The thing you should be looking at, though, the bigger picture, synthetically, is what are you actually getting rid of? So I'm now getting rid of an oxygen and a phosphine, and then I'm playing connect the dots. So if I get rid of the O and get rid of the phenylphosphine, or the phosphine, the phosphorus with the three phenols, connect the double bond from that carbon to this carbon. So you can almost think of this as the reverse of ozonolysis. So whereas ozonolysis would break a pi bond and give you a carbonyl, this is we take that carbonyl and regenerate a pi bond, carbon-carbon pi bond. Okay, so again, this one, geometry didn't matter because we had identical groups. And the last one, so in this case, the I is here just to emphasize that it's going to balance out the phosphine with a positive charge. So in this case, we're going to still get a Wittig reaction, but note that it attacks the aldehyde, and that this group is just serving as a withdrawing group on here. So this was acting almost like that same ester group that we had, but notice it's on the aldehyde, so it's not like having a withdrawing group on the actual phosphine molecule. So not sure what to really tell you to emphasize, because if you haven't figured this out already by looking at these examples, there's a little bit of ambiguity, a little bit of uncertainty. So I'm not going to emphasize too much about memorize exact details. I do want you to recognize, again, the electron withdrawing groups effect on the formation of the trans product, the E product. The rest of it, I mean, you could just tell that on these sort of guesswork to a certain point of how big something is. So I'm not going to make you memorize just how to do that. Okay. Key thing then, the take-home message on this, the two reactions. The hydrazone can undergo basic reduction where you end up with an alkane, and the Wittig reaction, you take a carbonyl on one side, a carbon double bonded to a phosphorus on the other, you get rid of the O of one, the phosphorus the other, and you connect those two carbons to a double bond, and you have your product. So this is the next to the last podcast. Hopefully it went well, and I will see you at the final one, hopefully very soon. Thank you. Bye.